In this video, we will learn about how a 2-input CMOS NOR gate works. Here is a circuit schematic of a 2-input CMOS NOR gate where we have two transistors P1 and P2 connected in series, which will act as pull-up network. Both are PMOS transistors. Two transistors N1 and N2, both are NMOS transistors which are connected in parallel. These two transistors together acts as pull-down network. We have two input connections. Since it is a 2-input NOR gate, both are named as A and B. A is connected to P1, B connected to P2. Similarly, A connected to N1 and B connected to N2. This is how a simple circuit schematic of a CMOS NOR gate looks like. And here is the expression for a NOR gate, which is A plus B the whole bar. And this is a symbol of a NOR gate. And here is a truth table. We have two inputs which are A and B. Therefore, we have four possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. The corresponding output for the possible input combinations are given. Let us verify one by one. So first, let us choose the combination A is equal to 0 and B is equal to 0. We very well know that when the input is 0, PMOS transistor switches on and NMOS transistor switches off. So for this combination, we have A is equal to 0 and B is equal to 0 as well. Therefore, transistor P1 and P2 both will be on, but the transistor N1 and N2 both will be off because the inputs are 0 and 0. Therefore, we have a continuous path from VDD to Vout through the transistor P1 and P2 because both the transistors are on. So what happens? The load capacitor at your output starts charging itself to VDD. Therefore, your output will be equal to 1. Now look into the truth table. Transistor P1 is on, P2 is on, N1 is off, N2 is off. Since both P1 and P2 are on, we have a path from VDD to Vout. Therefore, your output is going to be 1 because charge at your load capacitor is equal to your VDD. When you equate to your logic values 1 and 0, your output should be equal to 1. So, this is a first combination for 0, 0 where your output is 1, which is verified. Now, let us look into the next combination A is equal to 0 and B equal to 1. When A is equal to 0, P1 transistor is on. When B is equal to 1, we very well know that PMOS transistor switches off. Therefore, there is no connectivity from VDD to Vout because only P1 is on but P2 is off. On the other hand, look into the pull down network. Since A is equal to 0, transistor N1 is off but B is equal to 1, so the transistor N2 is on. Now look into the figure. We have a path from Vout to the ground through the transistor N2. So there is a path for the load capacitor to discharge its charges. What happens? Your output goes to 0. Now look into the combination. P1 is on but P2 is off. And similarly on the pull down network, N1 is off but N2 is on. So what happens? Through N2, the charges stored in your load capacitor discharges. Therefore, your output will be equal to 0. Right now, it is verified. Now, let us look into the third combination of 1, 0. When we look into this combination, A is equal to 1, B is equal to 0. When A is equal to 1, transistor P1 is off. When B is equal to 0, transistor P2 should be on. In the pull down network, when A is equal to 1, transistor N1 will be on. Since B is equal to 0, transistor N2 will be off. This is what given in the truth table. P1 is off, P2 is on, N1 is on and N2 is off. Now look into the logic. There is no continuous path from VDD to Vout. Therefore, the capacitor cannot charge. On the other hand, there is a path existing from Vout to the ground through the transistor N1. So therefore, if there is any charge stored in your load capacitor, there is a possibility that it can discharge itself through the transistor N1 to the ground. Therefore, your output goes to 0. Okay, so this option of A is equal to 1 and B is equal to 0 leads to the output 0. It is verified. Now let us look into the last combination where both the inputs A and B are 1. When A is equal to 1, transistor P1 is off. When B is equal to 1, transistor P2 is off. When A is equal to 1, transistor N1 is on. When B is equal to 1, transistor N2 is on in the pull down network. So now again there is no continuous path from VDD to Vout. Right now both the transistor P1 and P2 both are off. On the other hand, the transistor N1 and N2, both the transistors are on. Therefore, right now there is a path from Vout to the ground through the transistor N1 and through the transistor N2 as well. So, it is very obvious that your output is going to be 0. This is what given in the truth table. Your transistor P1 is off, P2 is off. Therefore, there is no path from VDD to Vout. On the other hand, your transistor N1 is on and N2 is on as well. So, your Vout completely discharges to ground, leading to an output called 0. So, for the input combination 1, 1, your output should be 0. It is verified. Therefore, we have verified all 4 possible combinations of 0, 0, 0, 1, 1, 0 and 1, 1. So, we very well know that the CMOS logic structure will always give complementary output. Therefore, we can directly implement only NOR gates. So, if we want OR gate, you have to use an CMOS inverter at the output of NOR gate where the inverted output will be equivalent to your OR gate. Thank you and I hope this explanation was clear.